Hi everyone, welcome to this week's SF seminar, episode 11. Thanks for taking the time to join us. I'm Sony. I'll be hosting today's session. We are very excited to have Ali Behrouz with us today. Ali is a PhD student in the computer science department at Cornell University and also a research intern at Google Research. His work explores the design of deep learning architectures, especially in the context of long-range sequence modeling, with applications spanning from language to healthcare to neuroscience. Today he will be presenting his recent work titled Titans, Learning to Memorize that Test 10. This work proposes a new family of architecture that integrates fast and parallelizable neural memory with attention, enabling models to retain and leverage long past information effectively at the test time. We'll have the time for questions at the end, but feel free to drop them in the chat during the talk as well. And I thank you again for being here. We are really looking forward to your talk. I'll hand it over to you. Please get started.
Thank you very much. Hello everyone, it's so nice to meet you all, and thank you very much for the kind introduction. So I'm going to talk about our recent work at Python, and so basically when we published the work, we were somehow fortunate to get feedback from a diverse group of people in different sub area of machine learning. And actually we see that there are a lot of connections with these kind of models, and also there are so many different perspectives that we can see at a single mathematical formulation. So basically there is one mathematical formulation, but a lot of interpretations that you can have about that one. So when I was think about that, I was thinking that somehow it's a very good start, because if we look at all the advances in the past 20 years or even more than that, we can see that there are a lot of different perspectives. But also at the very abstract level, there are a lot of connections. There are a lot of mathematical formulations that appear at different concepts. So it seems that all these perspectives are connected, and somehow at different a period of time, we can see that different perspectives help us to improvement. So if I want to somehow summarize some of these perspectives, actually all of them are just my interpretation of literature. There might be wrong, and so there might be a lot of different perspectives in this area, but I want to mention a few of them. So basically, if we look at some traditional approaches like hop-field network, or for example LSTM, and these approaches, we can see that most of them are having something like memory perspective. So that they get inspired from human brain. For example, what we have learned in those kind of approaches is that we need to have long-term memory, short-term memory. We have forget gate, and also a lot of interpretation for the associative memory. So that's a lot of things that we can learn from that perspective. And actually it continues about it continues and resulted to so many different RNNs. And then we start somehow the matrix multiplication or transformers era, that most of the time we are focusing on how we can make different approaches more efficient, and also somehow see how we can model RNNs or traditional approaches in matrix multiplication format. And at the same time, there are some alternative perspectives that are helping us to somehow enhance the architectures. And for example, one of them is the dynamical system perspective. We can see that if we see the sequence as a dynamical system and want to predict the next one, it's very similar to how we want to model dynamical system. And actually we are learning a lot of things from that. For example, linear approximation can be surprisingly effective. And also we have the discretization like discussion in Mamba that somehow can extend the forget gate of like traditional models. Then we have this like discussion about local and global convolutions and all these things. So again, we are learning a lot of things about that. And then we have something like, again, a memory perspective, but somehow we want to also take advantage of what we have learned from the matrix multiplication and transformer era. So basically, we are adding a lot of things to some of the traditional perspectives about like this memory, and also, you know, about some of the concepts. Our interpretation and also our understanding has been changed over time, so maybe we want to like revisit them. So in this like talk, I will mostly focus on this modern perspective. And for example, the different things that we are learning from that, and different things that we are somehow adopting from the previous literature, for example, data dependent gatings, or for example, we have something like delta rule, which is more expressive memory management. And then we have something like TTT and Titans. They mainly argue about expressive memory architectures. And also there are a lot of different perspectives like online learning and test time training in, for example, Longhorn paper and again TTT paper. So basically, there are a lot of things that we can also learn and adopt from previous literature to the current our current understanding of RNNs. So before going into the details, let's like discuss about a very fundamental question, that what is learning and what is memorization. And actually answering to that, these two questions could be very, very hard. Let's like discuss about these two concepts in human. For example, one question is, can we really learn without having a short-term memory? Or can we really learn without like having any form of memory? And on the other hand, can we memorize without learning? So the interesting thing is that the answer to the first question is no. There are like a lot of studies that shows that, for example, when a person face some challenges for like passing the memory from short term to long term, or somehow stabilize the memory, then they face a lot of like challenges in learning process, and they cannot somehow learn new concepts. So usually the answer to the first question is no. But on the other hand, it's like very common that we can just memorize things. You can just memorize a lot of words in new language without like learning about their concepts, how they can use them, or different kind of things. So somehow the answer to the first question is no, and the answer to the second question is yes. So somehow it seems that memory plays a very important role in our learning process. So in the traditional like neuropsychology literature, there is a very interesting definition of memory and learning that I personally really like. And it says that memory is a neural update caused by an input. And then, given this definition, we have the learning process, which is defined as the process of acquiring effective and useful memory. So all the things that we are trying to do in learning process is to just see how we can compress the information and how we can put it in the memory and how we can manage our memory. So given this perspective, let's somehow see how we can define associative memory. So before that, let me like define associative memory in a very high level. And actually, it's the ability to remember the relationships between somehow related or even unrelated events and items and different things. And we can like think about that as a dictionary that we have like keys and values and want to like map them together. And so given like this definition of associative memory, basically learning is the process of acquiring the mapping between keys and values. So basically, when we have this associative memory, the training process is that we pass the keys to the associative memory and ask it to like predict the value. And in the inference, we pass the query, we send the query to the memory and ask it to like give its corresponding value, or somehow like combine different informations that we have in the stored in the associative memory. So basically, that's generally the process. And given this perspective, what are RNN? What's what they are doing? Basically, they are just fixed size memory, and also some people also call it like hidden state. And what we are doing is just we try to compress the past data into this hidden state or memory. And the right process is that given an incoming data, we just compress it and add it to the memory. And when we want to like read something from the memory, we send the query and receive the corresponding information from that. So at a very high level, let's say that we have like this incoming data here. I'm not sure whether you can like see my cursor, but here we have like this incoming data. What we do is that we project the data into the hidden state, hidden space. And also we have this memory, as I mentioned, it's also called hidden state. And we project the memory into the hidden space and we just like add these two together. And we just put it into the memory and we just repeat this process. At any time that we want to somehow extract something from the memory, we multiply that by a matrix. And that's the process of like extracting information from the memory. So now let's get inspired from our brain, and why I really think that it's a very important process, because you know our brain is very effective and also it's very efficient. We can like learn with a few sample, we can like learn in like very efficient manner. And you know that's a great source of inspiration. It has evolved for more than millions of years, so why not just get inspired from what we are doing. And so one important thing about brain is that it's constantly memorizing. So you know we are just memorizing different events, what's happened to us, and a lot of things. And another thing is that we have a short-term and long-term memory. So let's revisit the definition of these two. So if we look at our short-term memory, we can see that it's very accurate. So let's just think about the information that you just got in the past 30 seconds. You might not hallucinate about that because everything is like very, very accurate. And if we want to like somehow remember something from very, very past, then we have long-term memories. And we might hallucinate or forget about some of the details. And actually, that's very similar to attention and also RNNs, because you know our short-term memory is accurate, and also attention is very accurate. It considers all the pairwise interactions between the tokens, so basically it's very accurate. And on the other hand, we have RNNs that they manage the memory with the cost of forgetting. So basically, in this perspective, we need to somehow. So I think, yeah, I got a message about someone in the waiting room. I'm not sure. So yeah, that's generally the main intuition behind Python, and we want to somehow use this short-term memory plus this long-term memory, and somehow combine attention with RNNs. And another thing that we need to like think about is that our memory is a neural architecture, and it's not a simple set of neurons. And what does that mean? Let me like elaborate more on that. Let's come back to the very high level of like RNNs. And as I mentioned, we have like this incoming data, we project that into the hidden space, then we have like this memory, we project that into the hidden space, and we just like combine them. And this is the main process. If we look at like the linear transformers, when we replace the softmax with a separable kernel, again, we can see that in the causal setting, it's like a linear RNN. And so in a very high level, again, the data comes, we project that, there is a memory, we project the memory, and we just like add these two together. And, you know, so basically, what is the difference between these two type of approaches? And we can see that the main difference comes from the memory expansion, or the fact that those kind of approaches use a vector as a memory, and now we are using a matrix as a memory in this type of architectures. And you know every other part almost is the same except the memory management part that I will like elaborate more on that later. But yeah, generally that's the main intuition. And so you know let's just simply generalize that. We can say that, you know, from a vector, we come to the matrix, and now why not goes to the neural architecture. And, you know, the main challenge here is that you have this incoming data, you project that, and everything is fine until now. What do you want to do with your memory? How we can like project the a neural network into the hidden space, and what should we do? So basically, it's very challenging, and it seems that we need to like have a alternative perspective to look at this problem. And one interesting perspective is that the data comes and we want to somehow store or compress the data into the parameters of like this memory module. And there are a lot of papers, even very old papers, that discuss basically these kind of approaches, these kind of ideas. And in the modern like models, TTT start this line of work that says like we have this incoming data and we want to train this neural memory, and we want to compress that into the parameters of this memory. And so basically, given these kind of perspective and the way of looking at this problem, as I mentioned, this memory is acting as an associative memory. And so, the question is, what objective function do we want to use for this one? And so basically, one simple objective for that one is basically a regression loss. And we have keys and values. We want to like map these two together, and so basically we expect the model to learn when we pass keys to the memory, we get like its corresponding values. And so basically that's what we are learning in the memory part. And so the next question is, what tokens should be remembered? And so a simple like approach to like treat this problem is to say that we want to like optimize this objective. What can we do? Basically, we can just like apply gradient descent or stochastic gradient descent to optimize this objective. And another interpretation about that is, humans are usually memorizing concepts that are surprising. And what does surprising mean here is that basically something that violates our expectation. And this gradient is like somehow modeling that intuition, because if xt, the incoming data, is like very similar to the past data that we had, and actually we can like fit a curve on all the past data, and also it can include x, then there is like no gradient for that. So basically there is no surprising metric in that. And if we like look at that, if we have like somehow have a very surprising token, basically it's very different from what we had. We have a very large gradient here. So basically it's somehow modeling the surprise metric. And the main problem with that is sometimes we might get a very surprising token because the concept or actually the context is like changed. And the initial token is very surprising, but the amount of surprise is a lot, and cause the model to have like less surprise metric for the incoming tokens in the sequence. And the way that like we try to model this process is using gradient descent with momentum. So basically we add this momentum. And so basically what's doing here is that we have this past surprise. Basically we somehow break this surprise metric into two parts. One is momentary surprise, which is the amount of surprise getting from the incoming data. And another one is the past surprise, is the amount of the surprise that we get from the previous tokens, or like previous closed tokens. And somehow, we are controlling the effect of past surprise and this momentary surprise using parameters theta t and eta t. And one like fair question here is that, let's say we have outlier data. So there's a noise in the data and it's like very different from the past data samples that we have seen. And, in that case, the momentary surprise would be very large. And so it seems that our model is like very sensitive to these kind of approaches, these kind of like scenarios. And this theta t here can act as like a gating for this momentary surprise. And if the data is like noisy, we have like large surprise, but also the model is learning to how weight this surprise in a data driven manner. And also based on the context, it can like decide whether we want to like store this data or not. So basically the way that we can like interpret this data t is like a gating for that momentary surprise. And also we have like this gating for the past surprise, because the context might be changed, and we don't need to consider the past surprise in our scenario. So basically we can just like set eta t equals to 0 and so on and so forth. So basically that's the main idea about how we can decide what tokens should be remembered. And now the question is what tokens should be forgotten, or for example, how we can somehow manage our fixed size memory better. And so basically the main idea here is that we can add regularization to this formulation or the loss function that we have, and basically it becomes an equivalent formulation of weight decay in this scenario. So here we have like this weight decay part when alpha t is equals to 0 or is close to 0, then it means that we want to like retain all the past information. And if it's like close to 1, it means that the context is changed, and so we need to like erase all the memory or something like that. So basically that's the forgetting part. And so there, in my opinion, there is a very interesting like difference between these specific forget gate and also the past forget gates, for example, in Mamba 2 or gated DeltaNet. And that is like, let's say that we want to erase our memory. And in this case, we can see different behaviors between these two gatings. In the Mamba 2 and gated DeltaNet, the gating part basically removes the memory and treats the incoming data as a first ever seen token. So basically the past data is just removed, and what we have right now in the memory is basically the multiplication of keys and values. But in this case, we remove the past memory or the retention. I mean, in the retention part, we don't retain the past memory, but actually we use what we have learned from past data to measure the surprising amount of this incoming token in XT. So basically here we can see that we still use empty, the past state of the memory, but actually we don't like retain past information when we want to like go to the next step. So that's like main difference between these forgetting and also another modern forgetting gates in like modern RMNs. So now the question is like how we can train this process. I mean, we have seen that how we can like design this neural memory, and now how can we like can we somehow like train it in a fast parallelizable manner or not? And based on what we have here, we can see that the process is not like very simply parallelizable. And actually one way to like make this process parallelizable is to use the idea that is also proposed in like various studies in like DeltaNet, or for example also discussed in the TTT paper, that the idea is we can like chunk the sequence into some subsequences, and then we replace this gradient part with the gradient with respect to the last state of the previous chunk. So basically, if we do that, we can like calculate all the gradients of the next chunk at the same time. And so basically, if we call all if we call this gradient as ut and replace it in this like formula of surprise, we can see that it's like linear, and basically we can like calculate it using associative scan or matrix multiplication that I will discuss in the next one, next slide. But and you know, basically one thing that we know is that it's like parallelizable. So you know, that's the main trick for making this process fast. And you know, we need, if we want to like take advantage of like what we have in like modern accelerators, we need to write this process as a matrix multiplication. And so basically we build on the work of TTT and extend this recurrent formula for the gating part. So basically, if we have this gating part, we can like just expand this recurrent formula, and then we can obtain this recurrence that we have, this actually formula that we have here. So the calculation of the first part is very simple. We need to see how we can write this second part in the matrix multiplication format. So basically, for the sake of clarity and also simplicity, let's assume that our memory is like a linear matrix, and everything would be the same. But let's assume that it's the linear matrix, and the gradient in that case would be simply just W0 times KT minus VT times XT. Basically, this one is also key in the training part. So if we do that, you know, we can just like all the values for theta I can be just like diagonal values of a matrix. So basically, we have this matrix theta B that its diagonal values are theta I, and also we have like another matrix like B, which is diagonal values is the multiplication of all past, you know, 1 minus alpha j's. And also the gradient part is just a very simple part. We can just like write it as a matrix multiplication, because we can replace just one vector of KT with the matrix of keys, and also one vector of VT with the matrix of V's, and similarly here. So basically, this term that we have here can also be reformulated as a matrix multiplication format. And you know, that's a general idea about how we can like train this process. And
we have a question in the chat regarding your previous equation.
uh,
Yeah, I think
yes, yeah, you are right. Actually, yeah, actually, this t minus one should be like t prime. Yes, sorry.
Okay, thank you for your clarification.
And so yeah, just as a like quick recap of what we have seen right now is that like we see that how we can like learn, and how we can learn the memory, train the memory, and how we can like design an effective long-term memory with a good memory management, and also how we can train this memory in a parallelizable manner with matrix multiplication format. And you know, the next question is how we can incorporate this short-term and long-term memory. And you know, at the end, we will talk about how does it work in practice. So as I mentioned, our perspective was somehow using attention as a core module for the short-term memory, and then use the RNN module as long-term memory. And you know, the question is how we can combine these short-term and long-term. And actually, it's not even very clear in like neuropsychology or neuroscience literature, because we still don't know that how they're working together. So here we do not have like that great source of inspiration that I mentioned. We don't know that how these things are actually connected, and how like they are helping each other. So we try to like discuss different kind of combinations, and actually some of them are already known in the literature. So the first one is like memory as a context. And what is the intuition behind this architecture is that, let's say that we have like this incoming data, and we pass this incoming data to our long-term memory to get the relevant past information. So when we get that, we somehow concatenate that to the initial sequence that we had, and then we pass it to the attention. And then the attention can decide whether for this specific context that we have, whether we want to attend to the past data, or whether like the current context is more important. So basically in the first phase, we see that this long-term memory is helping the short-term memory, which is attention. And in the second part, we want attention to help the long-term memory and somehow filter irrelevant data, or some of the data that we do not need to like focus on. So basically we pass the output of the attention to the neural memory to update it, and we just like combine these two for the final prediction. So another part that we have in our architecture is basically the persistent memory part, which are some data independent weights that are learnable. So basically there are a lot of interesting studies that discuss these kind of like techniques for enhancing the architecture. And actually, the intuition was very like connected to our architecture that we had. We try to like discuss different perspectives, and why we are adding this persistent memory. But the fact is, as I will discuss in the abbreviation study, we can see that it's not very that much important, at least in our architecture. The main reason that we like put it in the final architecture is that it somehow is the last piece of the puzzle for the architecture that we are discussing. Because we are saying that we have like this long-term memory, we have like this short-term memory, and actually we need the persistent memory that somehow encode the knowledge of the task that we are trying to do. So basically these additional tokens can act as those persistent memory. And as I mentioned, there are like different perspectives to that. The Himba paper, if I pronounce it correctly, the Himba paper also discussed these data independent weights as a meta tokens. The attention sync also discussed that. There's a lot of works that discuss like this idea. There's another paper that we cited in the paper, Titan's paper. I forgot its name, but actually they are also discussed how we can see MLP of transformer architectures as a persistent memory. And so basically we can just like add additional tokens in the initial part of the sequence and pass it to the attention, and they show that like it's more powerful and better. So there are a lot of perspectives that can like somehow show that this approach is like effective. And so that's also in our design. So that's generally the design that I mentioned. Another way of like looking at short-term and long-term memory is that we can look at that as a different branches of memory, where we have like when we pass the data into like RNN as a long-term memory and attention as a short-term memory. And so basically here it seems that we are using like different heads with different architectures. So one head is like the RNN one, and another one is like the attention one. Actually, they are somehow hyper heads, because for each of these architectures can also have multiple heads as well. And so basically, the main idea is that the data goes to the long-term memory and also goes to the short-term memory, and then we just like combine these two. And so basically, it's like a memory as a gate. And so that's another type of architecture that we can somehow combine these two. And actually, this one also discussed in several papers that how we can combine attention and also RNNs, or for example Mamba models in this manner. So this one, as I mentioned, is another way. And finally, the last one, which is like the most popular way in the literature to combine this neural memory and attention, is like a layer-wise hybrid models. So memory as a layer. The data goes to either like short-term or long-term memory, depending on the design, and then the output goes to the next type of like memory, and we just like repeat this process depending on the design that we have. You might like use several layers of memory and then goes to the attention, or vice versa. So generally the main idea is that we just like put them sequentially in the memory as a gate. We put them as like two different branches, and like in the Mac architecture, which we like focus more on that. The main intuition was somehow use kind of architecture that somehow combine these two in a way that both of them are like helping the other one. So yeah, so basically we see that how we can like combine these two. And now let's see what we can get in like experimental results. And so basically in the experimental results, we have mostly focused on like language modeling and like these common sense reasoning tasks. So the first part is that the one interesting thing that we observe is that like when we use like two-layer MLP as the memory, or in other sense we use deep memory, we can see that the model is like very powerful, and even a model without any attention, or only the long-term memory one, in some of the cases can beat hybrid models. And that's just one takeaway from our experiments. And another one, which in my opinion is very interesting, is that this memory as a layer is the most popular way of combining these architectures. And these results cannot be somehow very generalizable, and so basically we should like say that for all architectures. But at least in our case, one thing that we have observed is that the two type of architecture of memory as a context and memory as a gate are performing better than memory as a layer type of architecture. And that's another interesting takeaway that in my opinion we had. Another thing is the our experimental results on long context, or the ruler benchmark. So basically, we can there are some interesting, in my opinion, takeaways that, for example, momentum is very effective for longer context, and somehow it helps to better manage the memory. And so we can see a huge drop in the performance of like long-term memory when we remove that momentum. I will discuss that later in the application study. And another thing is that this deep memory is also very important. And if we just like replace the long-term neural memory with like a matrix, again, we can see a very considerable amount of performance drop. And finally, another thing is that, again, architecture, it seems that architecture matters in hybrid models. And so basically, we have seen like better performance in memory as a context type of hybrid models, instead of like memory as a layer ones. Another thing, another experiment that we had was like experimental results on long context of Bobby Long benchmark. And so basically the data set is something like a needle in high stack style state tracking. There are some facts hidden in like very long sequences. And so there's a final question that asks the model, for example, where is something, and the model need to all find all those facts and um, answer to that question. And so before like discussing the results, I need to like emphasize on two important points here. And one is architecture in this benchmark matters a lot. And if we just like simply change our Mac architecture to, for example, memory as a layer, or for example, change it to memory as a gate, we can see that the performance drop. So you know, I do not have the results here, but basically, the performance is like better than comparable models like Mamba or, for example, RMT in some cases, but we cannot see this scaling of like sequence lengths for those kind of architecture. So this memory as a context type of architecture matters a lot here. And another thing is that the small size models like Titans, Mamba, and also RMT are fine-tuned for this task. And basically, we just like follow the benchmark for this experimental design, and we also fine-tune the Titans for this task. And so the interesting part is that like they can like scale to longer contexts. Unfortunately, after like putting the paper on archive, we realized that we didn't mark the 2M the 2M length sequence lengths here, but basically it's almost fair pattern even for the 2M, and for 2M we can see that the performance is like relatively high and better than 90%. So we can see that it's like fairly scale with the and can perform well with the sequence lengths, and can somehow do this specific task of Bobby-Long benchmark even with the context lengths of like 2M or 1M and something like that, and it's like performing better than some ultra large models. Finally, we have this like evaluation study that I will like mostly focus on my takeaway from this evaluation study. So one interesting part is that, again, we can see that this memory as a context and memory as a gate are like performing better than memory as a layer, and at least in our case. And it's very interesting because most of the literature is focusing on the last part, and probably it's like it could be a sign that we might need to reconsider like different type of hybrid versions of like memory and like attention. And the interesting results that I can also like discuss here is that it seems that there is no free launch architecture here, because we can see that this memory as a context is like very good in long contexts, and it performs better than the other two. It's very fairly close to like reasoning task on average. And actually in the language modeling, this memory as a gate perform much better than this memory as a context. So it seems that there is no like free lunch, at least between these three type of hybrid architectures. And also regarding the long context, it's here we have like the ablation study on momentum. We can see that when we remove the momentum, the long context in ruler benchmark drop a lot. And also the linear memory, we replace our deep memory with the linear memory one, and we can see that again there's a huge performance drop in this case. Yeah, and also as I mentioned, we have like this persistent memory. We can see that there's no significant changes, but as I mentioned, at least it's like improving the performance a little bit. Thank you very much. If there's any question, I'd be happy to discuss it. Thank you.
We have one question in the chat.
Honestly, we didn't try those. That would be very interesting to see, like what would happen. If I want to be honest, uh, yeah, our expectation was somehow like those tasks might be too simple to uh, somehow deliver the messages that we want to like deliver. But yeah, unfortunately, we didn't try that. That would be very interesting to see whether like our guess was like valid or not. Yeah, so for basically for the code base that we have like implemented this in both JAX and part PyTorch. For the JAX one, we do not use any like Palas implementation, and also for the PyTorch one, we are using some like uh, you know optimized kernel for the inference to like handle those efficiency part of the model. But yeah, that's just for that specific part. We do not have like a very highly optimized implementation for the PyTorch. And for the JAX one, actually, my experience was somehow it's like fairly fast, but it's not as fast. We have some like discussion in the paper as well, but it's not as fast as like a very good implementation of like modern RNNs, but it's still fairly fast. And also the plan is to like open source the implementation, but if I want to be honest, I'm not sure about the exact date. I hope that like we could do that at some.
Before the next question, I have a question. So regarding the implementation, I think you have the speed comparison in your paper. Since you only have like JAX implementation, did you measure the time in JAX in TPU or on GPU?
So basically, for the comparison of the training throughput, we have like compare all the models in the PyTorch implementation, but yeah, that we don't like we didn't like implement all those approaches in the JAX and like compare those. So basically, that one is like on the GPUs and the PyTorch implementation.
So you compare both model on GPU. So you use the JAX version of Titans and measure the speed on GPUs and
Yes,
report.
yes. Everything is on GPUs for the training tool.
Yeah, do you think like JAX is inherently better than PyTorch to implement this type of model?
I think so. As I mentioned, I think basically one thing that we have like seen is that like the JAX code is like fairly fast. So as I mentioned, that was the main reason I didn't like focus on this kind of this optimized implementation of the model in PyTorch. But yes, actually, my interpretation is that like JAX is like fairly faster in this kind of model.
Yeah, I was also wondering, would JAX implementation be much faster on TPU than on GPU?
Uh, if I want to be honest, I didn't like, I didn't fairly compare these two. Uh, Honestly, I'm not sure exactly about the answer, but my guess is that probably yes.
I see, I see. Because well, my friend said on TPUs, like a scan is like really fast on TPU. But I think Zhixuan previously mentioned that on GPUs, if you use Jack, you still need to write some kernel for it, otherwise it's slow.
Yes, yeah.
Yeah, thank you for your answer. Maybe we can go to the next question. Maybe you can read the question so that
Um,
yeah.
I think the next question is I have a question on the mini batch size. How do you select the mini batch size? Is there a trade-off between efficiency and performance? Yes. So basically, as we discussed in the paper, we are building on the work of Python, sorry, TTT, regarding the mini batch style training. And so we didn't like highly focus on the efficiency of that part because already in the TTT paper, there is a very nice plot that shows that when you increase the mini batch size, and then you have a fairly faster model, but the performance also drops. So, basically it's like a trade-off between there's a trade-off between efficiency and also effectiveness of this model. And, even theoretically somehow it makes sense because in these kind of like models, contrary to the linear models, this mini batch type of training is like an approximation of the actual RNN or recurrent formula. And so when we increase the mini batch size, we are approximating that part more somehow. That's the reason we can see performance drop if we use like ultra large mini batch size or somehow increase the mini batch size. And yeah, so that's basically this one. That basically there is a trade-off between these two. I hope that I answered question. If it's not, please let me know. And so I think the next question is, where does persistent memory come from? I mean, it's retained between tasks. So I'm not sure whether I understand your question correctly. Basically, these are like persistent memory, or they are some learnable tokens that we just like concatenate them to the context. And yeah, so basically we are just concatenate them to the context. And one of the interpretation of uh, this concatenation of these learnable input independent parameters is that they are somehow storing the knowledge about the task that they are doing. But for example, we didn't like perform some experiments on tasks that require, I mean, multitask or different, having like different scenarios or having different tasks to see whether like this interpretation is correct or not. But yeah, that's generally, I hope that I answered that question. And did you observe any difference in training stability or maximum possible learning rate between your model variants? Uh, Honestly, I don't remember that we face like huge challenge of like stability of I mean different challenges for these models. Actually, somehow some of them needed to some stability techniques to somehow make them more stable during the training for longer context. But yeah, as far as I remember, most of them are somehow the same. I mean, combining the hybrid variants, I mean, the attention and neural memory somehow didn't affect the stability part that much. Uh, Persistent memory is implemented. So basically, let me, sorry, I think So let me use this figure to discuss. So basically, we just like add additional tokens at the beginning of the sequence. And basically, all these tokens are learnable parameters. And, they are not like inputs or context dependent. They are simply just learnable parameters that we add at the beginning of the sequence. And there are some different interpretations for that. For example, one is there are a lot of studies that says attention focus more on the initial tokens. So one way to improve that limitation is to like add additional tokens in the beginning of the sequence. Or for example, there is another interpretation that these learnable parameters are acting very similar to MLP layers after our block. So basically, uh, another way to look at the MLP layers is that, let's say you have like two layers, it would be something like W times that W1 times W2X. And that's very similar to attention because, the WX1 is somehow modeling the multiplication of Q and K. And then you have the nonlinearity and then multiplication by V or another W. And so basically, that's very similar. That's another interpretation of MLP as attention. And when we have that interpretation, basically we can like combine these two. And instead of, for example, ReLU activation, we can use softmax. And in that case, we can just like combine MLP layers with attention. And instead of having additional component of MLP after attention, we can have some learnable data independent parameters at the beginning of each sequence that are shared.
I was wondering, for each layer, you have different set of parameters for this persistent memory.
Yes, they are not shared between layers.
I see. Thank you.
They are different. Yes. So there. Yeah. So basically, these one point in the chat is like it's like similar to having a lot of BOS tokens. So that yes, that's correct. But they are actually learnable. So we are adding additional BOS tokens, but learnable BOS tokens. That's- So there's another question that do you have an explanation why the momentum is so important at the mechanistic level? The inner loop is not really a standard ID optimization problem with a well-defined objective. So I imagine the reason it helps may be different. Basically in the paper, one thing that we argue about that, if I want to be honest, I do not have a very clear answer for uh, why it's very effective at the mechanistic level. But in the paper, one thing that we argued is that why we think that, for example, deep memory is important is because in the inner loop, one thing that we are doing is to we are trying to somehow learn the mappings between keys and values. And given that perspective, there is a pattern between keys and values that we are trying to learn. And, a single matrix might not be a universal approximator to learn all the patterns, all the complex patterns. And when we have something like an MLP, then it's like universal approximator. And given that perspective, a gradient descent might not be enough to converge to the converge fast to the optimal point. So momentum somehow helps to converge my guess is that momentum is like helping to converge fast to the optimal point of the mappings between keys and values.
Yeah. I have a question. So, for the momentum turn, um, like recently, TTT has a video model claiming that TTT can have better temporal consistency in video generation. Do you think by adding the momentum turn and the temporal consistency would be further improved?
Um, yes, I was also like thinking about the same thing, but I do not have a very concrete answer to this question. But just my guess is that momentum, why not at the mechanistic level, but at the middle level somehow, not a high level and also not a mechanistic level. Momentum somehow is like a good is like an approach to somehow make the memory management better, somehow handling the effect of past tokens on the current token. So my guess is that in those scenarios it also should help, because it's like helping the temporal consistency to better manage its fixed sized memory. And so my guess is that it might help, but in those kind of architectures there are a lot of other components that also can affect the overall architecture. And there might be the case that adding this momentum would not be very effective that much, but my intuition is that it should help.
Yeah, thank you.
Do you still remember your final inner loop mini batch size? I think we use like 16, similar to the TTT. We use like 16 for the mini batch size. Yeah. Are there any known limitations that might appear for scaling Titans to tens of or hundreds of billion parameters? Would you make the arguments to companies with large training budget that they should be pre-training their next LLM with a Titan-based architecture, or are there fundamental issues with this model scale? Uh, so honestly, we didn't like try larger scales. So everything I'm saying is just like my intuition, that these like the Titan type of model can be like very effective, specifically for example, longer context. But actually, there might be some challenges about like the training throughput, or for example, there might be some challenges, for example, for the stability of like the memory. And so we didn't like try for longer, larger models. And these kind of things are like um, I mean, these kind of things are somehow unpredictable. We need to like scale to see whether like they scale fairly or like not. But uh, these are the main experiments that we have done, and mostly are in the paper. So basically, in these scales, we see that they are like performing fairly. But yeah. Have you checked the values of the learned momentum parameters eta? If so, did you observe any patterns? Unfortunately, no, we didn't observe or even check the learned parameters of momentum. But generally, all the you know all it's a very interesting question to see. I mean, what would be the effect of like a momentum, and how they're shaping the parameters, and if there's any pattern for that. But unfortunately, we didn't. Uh, Somehow, yes. So the question is, could we interpret persistent memory as latent knowledge? And my guess is that yes, we can. We can. As I mentioned, somehow we are. I mean, all those additional learnable data independent weights are somehow performing very similar to MLP, as I mentioned. So similar to MLP modules, we can say that all these like additional tokens are somehow performing similar to latent. I mean, they're somehow storing the knowledge, and they can be interpreted as latent knowledge. Yes.
Does anyone have other questions? And since APS we don't have further questions, so maybe we'll end here. And thank you again, Ali, for the great talk and helpful discussion. It was really exciting to know about Titans from your perspective, and thanks everyone who joined and asked questions. So goodbye and see you.
Thank you. Thank you very much for having me. Thank you. Bye.